Hey everybody. Alright, so we're still talking about Chapter 8 and various reactions related to alcohols that are kind of in the oxidation and reduction category. Alright, so oxidation reactions increase the number of bonds to oxygen usually, or it could be like nitrogen and things like that. In this chapter it's mostly oxygen though. So if we're oxidizing a functional group, we're increasing the number of bonds to oxygen. That also decreases the number of CHs. If we're reducing a functional group, we are decreasing the number of bonds to oxygen, or it could be nitrogen or other electronegative atoms, and we're increasing the number of H's, right? So we did a whole bunch of kind of overview material last time. I'm not going to go through it all, but that talked about that, how we, increasing the number of bonds to electronegative atoms for oxidation. Reduction is decreasing the number of bonds to electronegative atoms. We kind of showed the overall process in terms of the oxidation states as we go from methane all the way up to CO2. So we're gradually increasing the number of bonds to oxygen. We also showed that for a primary alcohol it can be oxidized to an aldehyde, oxidized to a carboxylic acid, and then you can kind of reduce. So I show the reduction kind of going downward. And for secondary alcohols it's really easy. You just go from secondary alcohol up to a ketone, and then you can go back. You can oxidize the secondary alcohol to a ketone, or you can reduce the ketone down to a secondary alcohol. Also recapping from last time, we introduced hydride reagents. Hydride reagents, which are reagents based on H-, right, as opposed to proton, right? So hydride reagents are H dot dot minus, and these are reducing agents, and they reduce ketones and aldehydes, okay? As we mentioned last time. We talked about sodium borohydride, NaBH4. It's a nice mild reducing agent that easily reduces ketones or aldehydes to alcohols. We also talked about lithium aluminum hydride, which is a more aggressive, more reactive reducing agent. On paper it doesn't look any more reactive, but in the lab it is, and you have to be very careful to avoid potential fires and things like that. We showed some examples of all of this, reduction of aldehydes, reduction of ketones. We showed all this last time. And maybe the main thing is, mechanistically, how does this all work? NaBH4 is nucleophilic H-. I present this sort of simplified mechanism where BH4- is essentially nucleophilic hydride. And as a nucleophile, it's H-, it attacks delta plus, pushes electrons up, and then you get a temporary O- intermediate, and then it gets a proton from ethanol. Okay, so this is all from last time. So when I say simplified from book mechanism, the book presents a slightly different mechanism. I don't know. This is probably less correct than the book, but it's also really easy, and for the purpose of understanding this reaction, this is totally fine. We went on with more examples of reduction. Then we moved on to chromium, and that's kind of where we are now. Chromium reagents are used to oxidize alcohols to aldehydes and ketones and other things. And this is kind of where we were leaving off. Let's move the camera around here. So the reagents are all based on chromium-6, so it's chromium with 6 bonds to like oxygen and other electronegative things. And there were 3 reagents, and this is a good way to summarize them. PCC is the partial oxidizing agent. It's chromium with 6 bonds to things, O- and Cl, and the other double bonds. Pyridinium is this thing, it says pyridinium chlorochromate. And then we have, for full oxidation, we have CrO3, chromium trioxide, and sodium dichromate, which is Na2Cr2O7. So it's 2 chromiums, 7 oxygens, and a pair of sodiums. And basically, you know, I emphasize PCC and CrO3. The book mostly emphasizes PCC and Na2Cr2O7. I think this is easier to memorize, though, CR3. It really does the same stuff. So you have a partial oxidizing agent and a full oxidizing agent. And then we're this is really where we're ending up. There's 3 situations to be aware of that really gets you through most of organic chemistry. If you have a primary alcohol, you can do a single oxidation, which is like going from 1 bond to oxygen to 2 bonds to oxygen. Primary alcohol to aldehyde. That's a partial oxidation. You can also do a primary alcohol double oxidation, where you go from 1 bond to oxygen to 3 bonds to oxygen. And you can use CrO3, H3O. Or if you want, you can, as the book emphasizes, Na2Cr2O7, sodium dichromate. So this undergoes a double oxidation to the carboxylic acid functional group. If you have a secondary alcohol, you really only have an option of a single step oxidation from 1 bond to oxygen to 2 bonds to oxygen. And we'll just call it a partial oxidation, but it's not like you have an option. And for this, you can either use PCC or CrO3 and acid, H3O. You always need the acid for the CrO3, or also for Na2Cr2O7. Okay, so that's kind of where we are, and anywhere where we use CrO3, you can also use Na2Cr2O7, and that's just another little point. Okay, so let's move into the new material. Okay, so a couple examples of these reactions. We're still on number 5C. So 5 was on these oxidation reduction reactions, and C was specifically on oxidation. Alright, so a couple examples of these reagents. If we have a secondary alcohol and we want to oxidize it to a ketone, which reagent should we use, or does it even matter? So you can either use PCC or CrO3 and acid. I should also mention that we often omit the solvent. It is important for the reagent. The book, and we'll do it later, emphasizes the use of DCM as a solvent for PCC. DCM. What's DCM? DCM is dichloromethane. Dichloromethane, which is just HCHClCl. It's a very gentle inert solvent that's used for a lot of reactions. And DCM dissolves PCC, so that's why we use it. We often skip the solvents, that's why I put them in parentheses. But we'll get back to why DCM is kind of important in PCC reactions a little bit later. What if we're going from a primary alcohol like this one, and we want to oxidize it to the carboxylic acid? Whoops, sorry. We want to oxidize this primary alcohol to this carboxylic acid. Should we use PCC or CrO3? It looks like we're doing a double step oxidation, a full oxidation, so we would need to use CrO3 and H3O, and I'll put the parentheses around H3O. What if we want to go from a primary alcohol to the aldehyde? CrO3 or PCC? It looks like it's a partial oxidation, so PCC. And we use dichloromethane, put in parentheses. So here and there I will just omit it, but yeah, dichloromethane is the preferred solvent for PCC reactions. Solvents, you know, they often don't do anything really, and so it's not that crucial to memorize them or something. But if you have note cards, you might want to just write DCM on there. And if you see it in the book, they'll probably mention DCM also. All right. So what about this molecule that has a primary alcohol and a secondary alcohol? And let's just consider the output of this reaction, the product. In the case of PCC excess, we're implying dichloromethane, DCM, but we're just not drawing it. Or CrO3 excess. Excess meaning, you know, there's a lot of the oxidizing agent, so that it would, if there's two functional groups, it would react with both of them. What's the products of these reactions? PCC would, what would it do to the left alcohol? What would it do to the right alcohol? Well, left alcohol would get oxidized to a ketone. Right alcohol would be oxidized to an aldehyde. Okay, and what am I missing? I'm missing the benzene. Oh yeah, sorry. You know, the circle is a we do the circle thing for benzenes, but you don't know too much about benzene, so I'm gonna go back to the alternating double bonds. Yeah, you know, I don't want to jump ahead too much. So yeah, benzene for now we're just gonna use alternating double bonds. All right. So then, what would happen with CrO3 in excess? Left alcohol, right alcohol. What would happen? The left alcohol would be turned into a ketone, and the right alcohol would be turned into, with, you know, CrO3 being a full oxidizing agent, into a carboxylic acid. All right, cool. So that's a couple examples. Okay, so what is we're showing 5C. What is the mechanism of these oxidation reactions? It's a little more complicated than the really cool reduction mechanism. Remember the reduction mechanism with NABH4? But it's not that bad. Alright, so if I have an alcohol, I'll just use a secondary alcohol to make this easy. And I'm reacting it with CrO3. Just because it's easy to draw. It's all the same. PCC does the same exact thing. It's just, remember PCC has a more complicated structure, but it does essentially the same thing. What is the oxidation state of chromium? So inorganic metals and, you know, things, like chromium and other heavy metals, we can define the oxidation state as the number of bonds to oxygen or chlorine or anything electronegative. So it's 6. We already said that before. Cr6. Okay, so chromium Cr6. We have acid in the solution, which of course implies H2O. We have H3O. We have H2O. And oxygen is delta negative, delta negative, delta negative, delta negative. Chromium then is delta positive. Okay. So chromium is delta positive. What is oxygen over here? It's delta negative. Alright? So negative attacks positive. So this OH attacks the chromium and it just kind of attaches. So I'm going to circle a lone pair and then push onto the oxygen. Okay? It's a little congested there, but yeah, oxygen just attacks the chromium, breaks the double bond onto oxygen. You can pick any oxygen, doesn't really matter which oxygen. Alright, and what does that give us? So you just got to follow through on the mechanism. What happens when oxygen attacks chromium? Now we have our O. Still got the H. H is there, I just flipped it over to the other side. And then we have chromium. Now what's on chromium now? Well, we have two double bond O's. And an O minus. Okay? Right? When this attacks, we still have two double bond O's and we have one O minus. What's the oxidation state of chromium now? It's still 6. 1, 2, 3, 4, 5, 6. So it's chromium 6 still. Chromium 6 still, right? Anything else I'm missing? What's the charge on oxygen? When oxygen gave up its lone pair to attack, now we have 3 bonds to oxygen. It's plus. Okay? So the first, and where are we ending up? We're ending up with a ketone. Alright, so so far so good. We just attacked the oxygen onto chromium. So the first thing that happens now is really easy. We just take water and we steal that proton. So water is going to be a mild base. It's going to take the proton. So how many arrows in a acid-base reaction? It's 2. 1, 2. 1, 2. Okay? Alright, so that's really easy. What do we get then? Now we get the same thing minus that proton. I should say the book does this mechanism slightly different, but it's essentially the same thing. So I think my mechanism's a little easier, and I'm happy with the easy one. Okay, so we got this. What's our oxidation state of chromium now? It's still chromium 6, right? So the oxidation has not happened yet because we still have only one bond from carbon to oxygen. One bond from carbon to oxygen, one bond from carbon to oxygen. So coming soon, it's going to go from one bond to oxygens to 2 bonds to oxygen, right? And that's where this next step's going to be, all right? Okay, so now we have this proton, the CH, and now the oxidation is going to occur. So what I do is I just draw water again, H2O, and now what's going to happen is it is going to get this proton, and this is where the oxidation actually occurs. Water takes that proton. Now it creates a C double bond O, right? A C double bond O, and pushes onto chromium. Chromium is like a leaving group at this point. Chromium goes away, and we actually have one more arrow onto one of the double bond O's. Okay? So water attacks, grabs the proton, makes a double bond O. Chromium comes off as a leaving group. What's the product now? Well, with the proton lost, it makes the ketone. So the ketone is formed. And what is our what does chromium look like now? when chromium falls off, it looks like Cr double bond O, O minus, O minus. And what's the oxidation state of chromium? It was 6 here, now it is 4. So this is like a byproduct, it's not a major product. But yeah, ultimately chromium 6 gets converted to chromium 4. And why does this all happen? It's because chromium 6 is a little less happy and chromium 4 is a little more happy. You're going from a less happy oxidation state of chromium to a more happy oxidation state of chromium. One other thing about this, you can kind of think about this as it's almost like we have oxygen with a leaving group. It's kind of almost like an E2 reaction, right, where the water takes the proton, makes a double bond, kicks off the leaving group, kind of E2-like. E2-like. And then you get the product and the leaving group comes off. So it's kind of, it's sort of related to, well, the mechanism kind of looks like an E2 reaction, although in an E2 reaction you actually have a base, and water's not really considered a base. For this reaction it's good enough of a base to take off that proton. Okay, that is the mechanism of oxidation with CrO3. Okay. And also I said, what is the thermodynamic driving force? What is the thermodynamic driving force for this reaction? So most reactions have a thermodynamic driving force, like in maybe the bond energies and stuff. In this case it's kind of cool. It's the conversion of chromium 6 to chromium 4, which is less stable and more stable. It turns out that chromium 4 does a couple other things, and there's some weird inorganic chemistry that takes place. So chromium 4 is not even the most stable. It keeps going. The chromium 6 is definitely less stable, and that's kind of why this overall reaction occurs. Okay? Okay, so that's a pretty doable mechanism. You might want to step through it, and if you have index cards, obviously this would be a good full back of an index card, the mechanism of the CrO3. Okay, and the mechanism of PCC is the same thing. I'm going to abbreviate it a bit. Mechanism for PCC. It's just a different CR6, a different chromium 6. So I am going to just use isopropyl alcohol. The only difference, of course, is very subtle in the structure of the reagent. You have chloride, O minus, and then we have something called X plus, which is, if you remember the structure of PCC, X plus was that pyridinium thing, the benzene with the nitrogen and the hydrogen. So look back a few slides and end of last lecture, and you'll see the structure of what this X plus is. It's just a counter ion. Okay, so what do you think the mechanism is? Alcohol attacks, kicks electrons onto oxygen. Now we have few O minuses, but that's no big deal. Still got the O with 3 things on it. Charge is now plus. Something takes off that proton. In the case of PCC, you don't really have water around, so some mild base does this, and it might be related to the pyridinium or something, but not a big deal. It's just a base, B dot dot. Something takes the proton. Alright, now we got this thing, O minus, chloride, and then how do we finish it up? Now we take the proton off with mild base. Just like before. Base takes proton, make the double bond, attack, it goes to chromium, and then like onto the other oxygen. Of course, this is chromium 6, just like before. 1, 2, 3, 4, 5, 6. What's the end chromium thing look like? Chromium, O minus, chloride, something like that. It's chromium 4. So it goes from chromium 6, chromium 4, and then there you go. So PCC is essentially the same thing. The only difference is the structure of the oxidizing agent. Alright, and now we're on to the next topic, number 6, which is the synthesis of alcohols via nucleophilic carbon. Synthesis of alcohols via nucleophilic carbon. And this is going to be kind of like, remember how reductions, we did that two sections ago? Number 4, I think it was. How we did H minus, H dot dot minus, and it reduced ketones and aldehydes and stuff. This is kind of like that. Instead of H dot dot minus, this is R dot dot minus. R dot dot minus is going to be nucleophilic carbon. And I'm going to just go ahead and say star, 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 star. So this topic and the variations of it is going to be almost seen every quiz probably till the end of Organic 2. This is such a huge deal in organic chemistry, is the synthesis of alcohols, and also just the use of nucleophilic carbon. So it's R minus, R dot dot minus, as a way to make carbon-carbon bonds. This is a C-C bond forming reaction. Why is that so cool? Well, we haven't really seen much of that, like making C-C bonds yet. And when we have the ability to make C-C bonds, you can start making complicated molecules and like taking, crazy piece A, crazy piece B, and snapping them together, really, and making synthesizing molecules. So this is going to be a really cool thing. Alright, so overview. Good start is to just remember what we were doing with our reducing agents. Hydride. Reducing agents, remember those? NABH4, LiAlH4, remember that, all that stuff? Okay, so when we had like an aldehyde and we reacted with NABH4 Remember all that? And typically like ethanol or methanol or some alcohol, you would get a alcohol, right? And it was essentially, with our simplified mechanism, we just said, oh yeah, H dot dot minus is a reducing agent. H dot dot minus, remember that? There's the Mark simplified mechanism for this. And H minus attacks. Here and there I do these Mark simplified mechanisms to focus on the most important thing and not necessarily all, or like really silly details. Remember, we get that, and then how do you finish it up? Like, now where does the O minus get its proton from to make OH? From the ethanol. Right? That was the Mark simplified mechanism for hydride reducing agents. So what's this whole crazy thing with multiple stars, asterisks, going to be? It's going to be a variation of this, but where we don't use H minus, we use R minus, some other thing. So an example will be same aldehyde, but instead of H dot dot minus, what if we had like ethyl minus, which would be H2C CH3 minus, ethyl minus. Let's put quotes around it because there's a little more complexity to this, just as there's a little more complexity to this. But if you have ethyl minus, what would it make? And where would it attack? Carbon with a minus charge. Where's a carbon with a minus charge going to attack in this molecule? Well, we have delta minus, delta plus. Delta minus, delta plus. The carbon is delta plus, right? The carbon is delta plus. So yeah, this is going to attack there, kick the electrons up. I'm going to kind of draw downward, like I like to draw my mechanisms downward, and then we'll work our way back up. But when ethyl attacks this butyraldehyde, 4-carbon thing, what does it look like now? Now this is O minus. And what did we just add? 4 plus 2 should be 6, right? And we just added 2 carbons. Look at that. Okay, and then we have to get the proton from somewhere. Usually it's going to be a second step with H3O plus or H2O. Like a second step. It's going to be step 1, step 2. All right, and so what happens with the O minus and H3O? O minus grabs a proton, and now it becomes from O minus to what? OH. So 4 plus 2 is 6. 1, 2, 3, 4, 5, 6. Okay. All right. So this is the kind of the basis for this whole section, and we have a lot of little details to get through. Like, how do we make this? What does it actually look like? It's not just carbon with negative charge on it. There's got to be some other elements and stuff, right? And that negative charge looks a little funny. Let's fix it. Okay, there we go. Ethyl negative, right? Carbon, CH2, CH3. CH2's got a dot dot negative on it, and then it attacks ketones and aldehydes for now, and other things as we'll learn. So this is, as we'll say, very cool. This is CC bond formation. CC bond formation. And so this gives us the basis to start making more complicated molecules, taking molecule A, molecule B, and making molecule C, and building more complicated molecules. All right. Can start building more complicated molecules. There's going to be almost the entire basis of Organic 2 will be synthesizing more complicated molecules from less complicated molecules. And another word for building is synthesizing. All right, so yeah, we'll get into organic synthesis as a topic here pretty soon. A couple notes. This idea of ch2, ch3 ... negative, it's very unstable and reactive. Very unstable and reactive. And so it's pretty sensitive. When you do this in the lab, you have to just be very careful or you'll destroy this stuff. Why is it so unstable and reactive? Well, carbon with a negative charge on it is very unhappy. Carbon's not electronegative, and so carbon doesn't like having that negative charge on it. And so it's very, very reactive as a nucleophile and also as a base. So any water around will destroy it. So this requires anhydrous conditions. What does that mean? What does requires anhydrous conditions mean? Like special lab technique to destroy water or get rid of water. So you use ovens to heat your glassware up. Your solvent, the solvent. When I say conditions, I mean the glassware, the flasks, and all that kind of stuff, and also the solvent. So the typical solvent would be THF, which we talked about before. THF, tetrahydrofuran, remember that? It's a 5-member ether. So THF is that stuff, and it's you just have to dry it extensively, distill it, and do various things to get rid of any water. Because water, if this stuff, this ethyl minus, it's essentially ethyl minus, right? If ethyl minus sees water, it just rips off the proton and becomes ethane. It becomes CH3 gas, and it goes away. So the other thing is that even though these are very unstable and reactive, these like ethyl minus and stuff, we can still make them pretty easily, and it is a doable thing in the lab. So fortunately, we can make them from haloalkanes. Remember those? RX, things like Br, like ethyl. Like I can make this from ethyl bromide or bromoethane, right? So alkyl halides can be converted to these molecules pretty easily. Okay, so we're on number 6 still, nucleophilic carbon. Nucleophilic carbon, so it's carbon being nucleophilic due to the presence of a negative charge. There are 2 kinds of this, 2 types. So basically 2 types of metals that attach to the negative charge. One is called Organolithium. So which metal is attached to the carbon? In this case, it's lithium, right? The other one is Organomagnesium. organomagnesium. So we have organolithiums and organomagnesiums. And the organomagnesium has another name. It's also known as a Grignard reagent. Grignard. So it's a weird pronunciation, and it's French, I think. Grignard. The G is silent, and it's just kind of, yeah, I don't know. It's not Grignard. It's Grignard. Almost like there's a Y in there. That's how it is pronounced. Grignard. And so both of these types of reagents are organometallic. Both are organometallic. What does organometallic mean? Well, carbon with a metal on it. Carbon lithium, carbon magnesium. So we could say like CM. It's like a carbon negative, metal plus. That's a way to think about it, right? It's like almost like an ionic interaction, but it's a little maybe it's kind of in between an ionic bond and a covalent bond, but it's a carbon bound to metal. Alright, so as an example, how we make these things. So if we have a bromide, we react with lithium, 2 lithiums. This is how we make the organolithium reagent. And we use a solvent like ether or THF. Remember those? THF was the 5-member ring with the oxygen. So this is an ether, diethyl ether, right? Ether or THF. They're actually both ethers in terms of the chemical structure. But the bromide gets converted to lithium, organolithium. So it's propyl bromide to propyl lithium. And then we get a lithium bromide out. So that's actually pretty simple. The lithium inserts actually, no, let's ignore that. Okay, so that's basically what's happening. So we have two lithiums. One of them gets attached, the other goes away with Br. Okay, this is not as simple as like an easy mechanism. So no mechanism for this. There's no mechanism for this reaction. I mean, you might think, oh, lithium attacks and kicks it off, like an SN2 or something like that, right? Because you've seen things like that. It's like, oh, nucleophile, electrophile, SN2. This is not a SN2 reaction. There's no lone pair on lithium to go do attacking. This is a complicated mechanism, and we just say no mechanism. So every now and then, I'm just not going to even show you a mechanism, and this is one of those cases. All right. Okay. Let's see. I'm also going to say no water. It's no H2O, because H2O will mess all of this up really bad. Why is that? Because if this sees water, it will. If this sees water, like if there's water around in the solvent, the ether, the THF, it'll just take that proton from water and become propane, right? It'll become CH3, CH2, CH3. This is incredibly basic and incredibly nucleophilic and reactive. So this has got to be done anhydrous. That's why you say no water. Okay. All right. So what about another one? I'll do iodide, 2-iodopropane. We do 2 lithiums, THF. Now, if you don't say 2 and you say just lithium, that's understood. The 2 is just a stoichiometric thing. Yeah, just there you go. Now we have 2. I don't know what the name of this is. 2 lithio. I don't. I actually don't know the name of this. There should be a name for it. I just don't see it. I don't know it this second. And then lithium iodide. Okay, that's pretty easy. Take any halogen, haloalkane, and convert the halogen to a metal like lithium. All right. Okay, so what are these called? If it's a carbon with a lithium on it, these are called organolithiums. Organolithium. What's the other one? Organolithium and organo something else. EM. Organolithium, and then we have organomagnesium, right? Organomagnesium. Also called, has a name, it's French. Grignard. So what does the Grignard look like? It's similar. And I'm just going to draw a BR, for example. And for these, we don't need the 2, we just say like Mg and like THF. THF is a good general inert solvent for all these things. THF. Alright. So for magnesium, though, it doesn't just kind of displace the halogen, it inserts between the carbon and the halogen. And so it actually, the end result, it looks like MgBr. Notice how the bond goes from carbon to magnesium, and then Br is kind of out there. So it really just inserts. The magnesium just sneaks in there, inserts between the carbon and the bromium bond, atom, and the result is, you know, isopropyl MgBr, right? Okay, so this is a Grignard. All right, so what about tertiary? We always know, oh, tertiary are kind of weird. Whoops. Tertiary are kind of weird, right? Maybe they don't do SN2 reactions and stuff. Well, this is not SN2 chemistry at all. I'll use a chlorine for this example. Mg, THF. Now, of course, it has to be dry THF. Dry. We don't always just say that. It's assumed. Okay. Dry THF. Dry THF. Dry means anhydrous, no water. Okay. So, you know, we don't say that every time, but it's assumed. These things are very, very reactive, and if they see water, they just are destroyed instantaneously. So you always assume dry THF. All right, what do you think it's going to make? Tert-butyl, chloride. Where's the magnesium going to go? In between the carbon and the chlorine, and then yeah, you just get. All right, so these are Organomagnesium reagents, also called Grignard reagents. What are these called? These are called Organolithium reagents. Okay, so the difference, I guess, in structure is that the lithium is just attached by itself. It's monovalent, right? Lithium is a monovalent metal. Magnesium is divalent, right? Magnesium is in the second column of the periodic table, and it likes to bind to 2 things. That's why it inserts, and then you have like a carbon magnesium bromide, carbon magnesium chloride. Okay. Also, oh yeah, what halogens are allowed? Chloride, bromide, and iodide are allowed. Fluoride is typically weird, and fluoride does not do this. Okay. What other structures of these organometallics can we do? We have like primary, secondary, tertiary. What else can we do? So all like methyl works. Methyl is good. Primary is good. Secondary is good. Tertiary is good. Aromatic is good, which is like a benzene. These are all good. Okay, and so if I have an aromatic, like a bromobenzene, totally works. If I do magnesium, and this time we'll switch to ether, diethyl ether, totally works. Magnesium sneaks in there, and you get the Grignard, MgBr. Okay, totally works. It is always dry, but you know, that's not a detail we always say. In terms of the halogen, what are the good halogen? You know, what are the best and worst halogens? Iodide is the best, then bromine, then chlorine, and then fluorine is basically not good at all. Anything else? So yeah, overall, this is a general rule all the way through the end of Organic 2. Organolithiums are essentially equal to organomagnesiums. So there's not much of a difference in reactivity. They're relatively equivalent. In the real world, you know, beyond organic chemistry class, there will be some subtle differences. But for you guys, just, you know, assume that, oh, if I see a organolithium or organomagnesium, oh yeah, they do the same thing basically. They're nucleophilic carbon. They attack ketones and aldehydes and other things. We'll learn about more things they attack throughout Organic 2. Even there's more even in Organic 1. So, like I said, this is a huge, huge, huge topic. We're going to learn tons about nucleophilic carbon, and it's the basis for organic synthesis. Yeah, so really cool stuff. So yeah, overall these are equivalent in reactivity. By reactivity, it's like what functional groups do these things react with, and they're going to be relatively equivalent. Okay, so we're still talking about nucleophilic carbon, number 6, and we're on to kind of the structure and reactivity of these things. These are organometallic reagents. And so they are highly organometallic CM bond. The organometallic CM bond, as we talked about before, it's highly polar, meaning there's a lot of charge density on the carbon. It's negative, right? It's pseudo-ionic. Pseudo-ionic. So it's not exactly ionic, but it's kind of like, it has ionic properties. So if I say propyl, CH3, CH2, lithium, what I mean is it's kind of in structure the same as H3C, CH2, CH2 dot dot negative lithium plus. Okay? So those are kind of like, you know, it's kind of ionic. It's almost like a carbon with a negative charge, like I said. nucleophilic carbon, right? So it's sort of, you know, bonding is not always like discrete, you know, it's not like, oh, just this or this. It's kind of somewhere in the middle. It's like there's a little bit of a continuum between covalent bonding and ionic bonding, and this is it has sort of some of both properties. All right, so yeah, and so also if I consider like phenyl Grignard, oops, phenyl Grignard is Grignard on a benzene. It's kind of equivalent to that idea, right? It's almost like a benzene with a dot dot negative on it. All right, pseudo-ionic is a good way to say this. The other, and this is called. So, what do you think it's called? Is this a carbocation or what? It's not a carbocation. It's a carbanion. Called it carbanion because it's more anionic, right? It's negatively charged, right? The other interesting thing, if you compare like propyl bromide or bromopropane with propyl Grignard, what are the delta charges? This, as we learned, is delta minus and delta plus. This, it's actually more like a full negative, but in terms of delta charges in the covalently bound species, it's more like delta plus, delta minus, you know, if not full minus. But notice how you know, if and we actually we can go do this as a reaction. We just throw in some magnesium, and it kind of reverses the polarity. This is delta plus, delta minus, but the Grignard type reagent is like delta minus, delta plus, and this is nucleophilic. This is electrophilic. So this is like a substrate for an SN2 reaction. This is actually a crazy super reactive molecule that we can attack things like ketones and aldehydes with. Okay, so that's a little bit on the kind of structure and reactivity or properties. The structure of these Grignards. All right, cool. I'm actually going to rename C up here from structure reactivity to, I think it makes more sense to just call it structure and properties. Physical properties, right? Structure and properties is maybe the better word. Structure and properties. Okay. Alright, so then for D, organometallic reagents. Organometallic reagents are highly basic. I already said that. If they see a proton somewhere, they just rip it off because they're incredibly basic. Some of the most basic chemicals in the universe. So carbanion is very reactive as a base. Carbanion is very reactive as a base. How do we quantify basicity? Like if I'm considering a random organolithium, I'll draw it in this sort of anionic form, lithium plus Alright, so there we go. We have our little organolithium. I'm drawing it ionically. So it's benzene, CH2, CH2, CH2 minus lithium plus. How do we quantify basicity? Well, remember, we usually, if we want to quantify basicity, we talk about pKa values. pKa values are acidity, though, so there's not really an acidic proton here, right? So we talk about pKa of the conjugate acid, so the CH3 version of this. All right, so that's the way we do it. And if I consider water to do this calculation, I just assume water, and then of course this can take the proton of water, and so it's sort of like, okay, you can rip off that proton like no tomorrow. This is a very, very favored reaction. And then what do we get? Benzene, CH3. And what's the byproduct? OH minus. OH minus. Okay, and yeah. And what now to rate like how far this equilibrium is left to right, we look at the pKa values of these two things. What's the pKa of water? pKa is 15.7. And then we compare that with the pKa of this guy, of an alkane. And if you look on that chart I gave you, it doesn't have this specific molecule, but it has other alkanes, and it's roughly 60. Okay, so when we compare it, like if I'm trying to determine the K value, the equilibrium constant, it's going to be the difference of these. But it's not just the difference, it's 10 to the difference. So the 10 to the difference is like 10 to the 45 almost. So it's like a 1 followed by 45 zeros, right? That shows you how insanely favored this reaction is to the right. This is so incredibly basic that it's quantitative. This will completely go to the right, and then we form this. Okay, so these are incredibly basic. That's what I'm trying to say. Incredibly basic. Anything with a kind of low pKa, like 15, 20, or anything like that, will just give its proton up to this kind of molecule. All right. Now, this is also the same for Grignards. It's not just for organolithiums. Grignards are the magnesium thing, right? So, thus, it's really easy if you want to reduce. It's very easy to reduce a molecule like Rx, halogen. If I want to reduce a molecule like Rx to Rh, just remove the halogen. It's very easy to do that with a Grignard. All you have to do is make the organolithium or the Grignard, and then you just throw in some water and it's gone. So I'll show that on the next slide. Alright, so example, if I wanted to get rid of that bromine and leave it with a hydrogen, like that, so that assumes a hydrogen, right? How could I do this? 2 steps. Synthetically, I just say magnesium, THF, and then water. So what that does is it makes a Grignard, highly, highly, highly reactive Grignard, and then grab the proton because it's incredibly basic. That's a carbon with a negative charge. I can actually draw the mechanism for the destruction of this. I can either draw this ionically, like carbon minus MgBr plus, or I can actually just circle the bond, because the bond is incredibly reactive, and I can just go like that. Okay. Where does the MgBr go? It's MgBr plus, it's a ion, and then we have OH minus. That's all byproduct stuff. But yeah, so it's very easy to convert like a bromide to an alkane this way. All right. How about what if I want to attach a deuterium? Deuterium is a heavy isotope of hydrogen, and that's actually really easy. I can do this kind of thing too. So 1, 2 also. I'm going to draw it downward. I'm going to say, I'll use lithium this time. Lithium THF. Now I just make lithium. Make the organolithium. And then deuterium is essentially hydrogen with an extra neutron. And you can just use something called D2O, heavy water, deuterium oxide. Deuterium oxide, which is heavy water. It's just a variation of water that has an extra deuterium, extra neutron. I'm sorry. And would you ever make these type of things? It's because they're used in drug metabolism, and there's other studies where it's like you actually need to change a molecule to identify it easier, and there's a lot of reasons for this. I'm not going to get into that. Okay, so what's step 1? What's step 2? Lithium, THF in parentheses, D2O. Okay, so THF is the solvent you use. Sometimes we skip the solvent. So basically lithium and D2O. All right, cool. And what we just showed here is kind of a boring use of Grignards and organolithiums, showing that, oh yeah, we can destroy a bromide, or and incorporate a hydrogen or deuterium. Is not that exciting. The really exciting thing is the next section, which we'll start and finish next time. Synthesis of alcohols with organometallic reagents. Synthesis of alcohols, so making alcohols and synthesizing alcohols with organometallic reagents is a big deal, because this is going to open doors to all of the organic synthesis that we're really going to do in, the remainder of your organic chemistry education. As we said, in addition to lithium, organolithiums and organomagnesiums being basic, which are showing, oh yeah, they can be bases, right? Let's draw the arrow here, circle the bond. In addition to them being bases, they can also be nucleophilic. They are nucleophilic, so they attack carbons, delta negative carbons, and this is a huge, huge, huge deal. Let's just show a couple examples of this real quick. Okay, so if I have formaldehyde, if I have Grignard and formaldehyde, the Grignard can attack formaldehyde and actually form a CC bond. Okay, and we can kind of figure out the molecular structure and the formula by just basic arithmetic. 3 plus 1 should be 4, right? 3 plus 1 is 4. And to do the mechanism, I showed earlier that, oh yeah, we can just use the bond and attack. But another way to do it is just draw it ionically. So just kind of like this, negative, MgBr plus. I'm drawing it covalently. I can also draw it ionically. So it's basically 3 carbons negative. And this thing, of course, is delta minus delta plus, delta minus delta plus. The carbon's delta plus, right? The carbon, oxygen's delta minus, carbon's delta plus. And so this thing can just attack. So circle the bond. And form a bond from carbon to carbon. It's a CC bond forming reaction. What does that make? Yeah, it went from 3 carbons to 4 carbons, just like we said. And here's those 2 H's that we had on formaldehyde. HH, right? So now we went from 3 carbons plus 1 to 4 carbons. And then this is either water or acid, and this just, the O minus just grabs the proton. And what's the final product? It's a primary alcohol. So this aldehyde, this formaldehyde gets converted into a primary alcohol. 3 plus 1 is 4. Okay. Let's draw another one. They also attack aldehydes, like normal aldehydes. H2O or H3O. So this 3 carbon organolithium, and Grignards and organolithiums do the same thing. They also attack, in addition to formaldehyde, they also attack normal aldehydes. For this one, I'm just going to circle the bond, because the bond is nucleophilic. And then draw the intermediate and then the final product. So 3 plus, this is 7 carbons, 3 plus 7 should be 10. 1, 2, 3. 6 plus 1 is 7. So I'll end shortly. O minus. Okay. So 3, there's 7. 1 plus 6 is 7, so it's 10 carbons total. And then this just grabs the proton. So the O minus gets the proton from water, and you make a secondary alcohol. Okay. Now, of course, I can draw this either like this, or I can just say, how else could I do it? I could say, oh yeah, CH2 dot dot minus lithium plus, and then have the dot dot minus go attack. Either of those is fine. I can either use the bond, or just like I did up here, I drew the ionic complex, and it's CH2 minus goes and attacks. That's all the same. And in closing, I'll just draw one more real quick. Just a ketone. I did formaldehyde, I did an aldehyde. Let's just draw one on a ketone just to show that. Okay, there we go. Ethyl Grignard. Ethyl Grignard. Let's draw this. Kind of like this, I guess. Okay, there's step 1, there's step 2. Okay, so we have ethyl Grignard, ketone, and then water. What's the product? And what's the mechanism? Ethyl Grignard, cyclohexanone, it's a ketone, and water. So it's mathematically 2 plus 6 should be 8. And let's draw the mechanism in the intermediate. So the ethyl attacks the ketone. What's the intermediate look like? It's going to look like, there is my 6, and O minus, how many carbons do we add? 2. Alkoxide, O minus. And what is the product? After O minus gets the proton, it's just a tertiary alcohol. Right? 2 plus 6, and when we add a Grignard to a ketone, it always makes a tertiary alcohol. Okay, add to a ketone, you make a tertiary alcohol. What did we make when we added to an aldehyde? Let's just, I'm done basically, but I just want to show that in the last page. When we added a lithium to a aldehyde, what kind of alcohol is that? That's a secondary alcohol. Right. And when we added to formaldehyde, what kind of alcohol was that? Going back. Formaldehyde, we made a primary alcohol. That's an interesting point that we're done now. But that if you add to an formaldehyde, you make a primary alcohol. If you add to a aldehyde, you make a secondary alcohol. And if we add to a ketone, we make a tertiary alcohol. That's a good thing to keep in your mind. It's going to help you a bit. Alright, so some really fun stuff. We're done, and we'll continue next time with more of these Grignard and organolithium reactions to ketones and aldehydes, or formaldehyde.